Oke, Assalamualaikum warahmatullahi wabarakatuh. I am Farizana Badani and I am from class 6B. Now, I want to explain about sums and average of random variables. In this chapter, we will describe one important way in which the theory of probability provides a foundation for statistical inference. Imagine an experiment that can be performed independently and identically as many times as we please. We describe this situation by supposing the existence of sequence of independent and identically distributed random variable x1, x2, and we assume that these random variables have a finite mean u equals xi and a finite variance O2 equals var xi. The explanation about the weak law of large number. In probability theory, the law of large number or LLN is a theorem that describes the result of performing the same experiment in large number. By law, the average yield obtained from a large number of trials must be close to the expected value and will tend to approach the expected value as more trials are conducted. The weak law of large number, or also called Kinchin laws, states that the sample mean converges in probability against the expected value. Interpreting this result, the weak law states that for any specific non-zero margin, no matter how small, with a sufficiently large sample, there will be a very high probability that the average observed will approach the expected value. This is within the margin. It is important to remember that the law only applies, as the name indicates, when a large number of observations are considered. There is no principle that a small number of observations will coincide with the expected value or that the sequence of one value will immediately be balanced by another. For example, a single 6-sided roll of the dice yields one of the number 1, 2, 3, 4, 5, or 6, each with the same probability. Therefore, the expected roll average values are 1, plus 2, plus 3, plus 4, plus 5, and plus 6 divided 6. That equals 3.5. According to the law of large number, if large number of 6-sided dice are rolled, their average value, sometimes called the sample mean, will most likely approach 3.5, with precision increased as more dice are rolled. It follows from the law of large number that the empirical probabilities of success in a series of Bernoulli's experiments will be met with theoretical probabilities. For Bernoulli random variable, the expected value is the theoretical probability of success, and the mean of the variables, assuming they are independent and identically distributed, is the correct relative frequency. The next, the explanation about the central limit theorem. The central limit theorem is theory which states that if the sample size gets bigger, then the nature of the sample means distribution will get closer to the normal distribution. The center boundary theorem is, in probability theory, a theorem that specifies the normal distribution as the distribution or place the mean of almost any set of independent and randomly generated variables converge rapidly. The center boundary theorem explains why the normal distribution appears so common and why it is generally a very good approximation to the mean of the data set, often with as few as 10 variables. The standard version of the central boundary theorem, first provided by the French mathematician Pierre-Simon Laplace in 1810, states that the sum of average of an infinite sequence of identically distributed and independent random variables, if scaled appropriately, tends to be normally distributed. 14 years later, the French mathematician Simon-Denis Poisson began a continuous process of refinement and generalization. Laplace and his contemporaries were attracted to the theorem mainly because of its importance in repeated measurements of the same quantity. If the individual measurements can be seen as roughly independent and identically distributed, then the mean can be approximated by a normal distribution. The Belgian mathematician Adolphe Quetelet, 1796 until 1874, famous today for originating the concept of Hamiltonian or Kamoman, was the first to use the normal distribution for anything other than analyzing errors. For example, he collected army bus data, see the last figure, and showed that the distribution of recorded values roughly corresponds to a normal distribution. Such examples are now viewed as a consequence of the natural limit theorem. Histogram card, the histogram or bar chart showing the case measurement of 5,732 Scottish soldiers, published in 1817 by the Belgian mathematician Adolphe Quetelet. This is the first time that human characteristics have been shown to follow a normal distribution, as indicated by the overlapping curves. Okay, maybe that's all. I'm sorry for my mistake, and thank you for your attention. And last, see you. Assalamualaikum warahmatullahi wabarakatuh.